Hello, this is Dr. Lori. Welcome to this overview of statistical tests. In this lesson, we are going to be learning about a whole bunch of new tests. We've learned a few so far in our class, and I've outlined some of that here on the table that I'm going to be sharing with you. As we're getting started with this, one of the things that I wanted to do is to review some of the things that we already know. So first of all, in this particular topic, we really need to be solid on understanding the levels of measurement. So as a review, and I generally start here at the bottom, dichotomous is where you have two values for a particular variable. So you can ask the question, do we have at least two values? Nominal means, do we have at least three? And so it could be 3 or 4 or 10. Ordinal means that those 3 or more are in a specific order. They make more sense, kind of low to high, or disagree to strongly agree, that kind of thing. Then we jump over and we get to scale, and by scale we mean, are those adjacent values equally spaced? And by equally spaced, we just mean that each of the increments has the same degree of difference. And so height would be a great example of that, where each inch represents the same amount of distance. And then we have this interesting middle category. It's scale and it's ordinal, but these are ordinal variables that have sort of been promoted. In other words, they have so many categories that they start behaving almost like their scale. They aren't technically, and so we put them into this category. Or for scale variables that are not normally distributed and have a small sample. And so I've kind of included that here. We learned previously about the central limit theorem and how the larger the sample, the more a scale variable is going to be fine, even if the assumptions are slightly violated. So we have our levels of measurement, and everything that we do after this is built on the level of measurement. So last quarter we learned about graphs and summary statistics. The best graphs and summary statistics for all of these categories down here: dichotomous, nominal, and ordinal. A bar graph is a typical one. Pi can also be used, and we report the frequency or the number and the percentage for each category within those categorical variables. Up here for scale, the typical graph is a histogram, and we report mean and standard deviation. And then for this interesting middle category, and you'll see where this is going to start becoming important, we have a box plot, and we report the median. Instead of the mean, we report the median and the range, or the interquartile range, something along those lines. And so those are what we would consider to be the descriptive statistics that we would use to summarize each of those kinds of variables. Then we've started to learn about inferential statistics, and specifically we're going to be focusing on bivariate inferential statistics. And what I mean by that is we have some kind of a variable, and then we want to look at the relationship between that variable and some other variable, and I'm going to highlight those up here along this top row. So when we were first learning about inference, we learned about the one sample t-test and how we can take that histogram, that mean and standard deviation, and we can actually test it against a hypothetical value, some reference, some standard score, so to speak. We've also learned about the chi-square goodness of fit, where we may have a dichotomous variable or some kind of categorical variable with 3 or more categories. And for each of those categories, we can test whether whether the distribution is as we would expect, whether each of those categories has the percentage within each category compared to some either a reference population or some other way of deciding what we think that should be. So this particular column right here is something that we've talked about before. Now, I've never put it into a table quite like this before, but when I've done this in the past, the students a lot of times will say this has been really, really helpful. A lot of textbooks may have a flow diagram or a table that's just sort of like a line listing with the different variables. If you find that to be helpful, then definitely use that kind of a flow chart. But for those that have a hard time just memorizing large quantities of information, sometimes seeing how tests are similar to each other in a variety of different ways can also be helpful. So we've also learned, especially now that we've started talking about case control studies and cohort studies, we've talked about the chi-square test of independence. That's what TOI stands for. So the chi-square test of independence, and specifically also the odds ratio and the risk ratio. All of those can use what a lot of people would consider to be a 2x2 table. And you'll notice in this particular table, this graphic, we are in the column that has two groups, and we're in the row that also has two groups. So that's how to read this table and how these statistical tests are going to be arranged within the table. So I hope this is helpful to you. So anytime we have a dichotomous variable and that is paired up, if we're doing some kind of inferential statistics against another dichotomous variable, another two groups, so this would also be considered to be dichotomous, then the best statistical tests we have are chi-square test of independence, odds ratio, and risk ratio, depending on the study design. We've also learned a little bit, just touched on so far, and we'll be learning more later, about something called logistic regression. And this is where we have some kind of a not grouping variable, so a scale variable as a predictor of a dichotomous outcome. And so what I'd like for you to think of in general, the way we're going to use this table is that these levels of measurement over here on the left-hand side, these are our outcome variables. These are the disease, the dependent variable. We call them by different names. But in general, when we're looking at this beginning, the origin, this generally tends to be the outcome or the dependent variable. So if a person has a disease, yes, no, that would be dichotomous. If the outcome variable, on the other hand, is whether certain things contribute to a person's cholesterol level or their BMI or some other continuous or scale variable, then we would be up here on this top row. Similarly, if we had some kind of an outcome variable that was scale, but it's not normally distributed and we have this small sample, or we have something that's a ranking variable to start with, it's ordinal, but it has quite a few categories, something like a pain scale on a scale from 0 to 10, then we would want to use this shaded row. Now I've shaded this row intentionally so that we have a little bit of a distinction across the table. These two bottom rows tend to be very similar to each other. You'll notice we use a bar graph, a pie graph, n in percent, chi-square goodness of fit. So a lot of things are very similar. For these bottom two rows, it kind of almost doesn't matter if our outcome variable is dichotomous, nominal, or ordinal with just a few categories. And so we can use the same statistical tests and summary statistics for those. You'll also notice that I've shaded out in dark. If I could X them out, I don't have a way to draw in this particular setup that I'm using today. But if I could X those out, there are statistical tests that will do those, but we are not going to be learning those. So those grayed out boxes, we're just going to leave them empty. So our task today then is to start thinking about what are some of the kinds of statistical tests that go into some of these other categories. The reason that we've talked more about what goes on in this bottom category is that as we were introducing the case control study and the observational cohort study, we were thinking more about whether the outcome was dichotomous. So now we're expanding to have some kind of a scale or continuous outcome variable, and that would be most applicable to having an observational cohort or maybe even an experimental cohort. There are exceptions, of course, but in general, that would be the kind of study design that these would apply to. If you have a case control study, by definition, your outcome is dichotomous, cases and controls. So this would be less useful for that kind of a statistical test or study design, sorry. The other thing that I'd like for you to notice is that I've shaded a couple of these similarly to each other. And the reason that I've done that is that I want to draw, let's undo that. I want to draw some important similarities between them. The compare to reference and the before and after tests actually mathematically behind the scenes are identical to each other. And so we call them by different names because maybe we're looking at different things, or we may have a different set of questions that are typical for those kinds of tests, but mathematically they're the same. Also, when we're looking at the 2 groups and the 3 groups, those are very similar to each other. In fact, when we're looking at tests that only have 2 groups, often that's just a special case of this more general kind of statistical test where we have lots of groups, but this is a special case that only has 2, and so it simplifies things a little bit. And then when we're thinking about a scale predictor variable, so these are our predictor variables, when we're thinking of a scale predictor variable, the thing that I like to point out, at least on this top row right here, the statistical test that we will eventually get to is called simple linear regression. And in many ways, all of these tests along this top row, the one sample t-test and all of the other ones that I'm going to be introducing to you, are all the same test. They are all a linear regression. They're just dressed up in a different name. Remember, a lot of times when we're learning a new field, we're learning the lingo, we're learning the language so that we can say a certain thing. We can say one sample t-test and people know exactly what we're talking about. We can say chi-square goodness of fit, and we don't have to explain so many details about that particular statistical test because people have a common understanding of what that means. So right now we're learning the language, but keep in mind that mathematically a lot of these tests are very similar to each other, and it can be helpful to think about how those similarities make them similar, make them easier to remember in terms of what kinds of questions they can answer. So let's start off on this top row and let's talk about the one we know about. So the one sample t-test, basically what we do with the one sample t-test is we take a group of people, one sample, and we measure all of them on a particular variable. Remember, we're talking about a scale variable, a continuous variable. So maybe we measure everybody on their serum cholesterol. And what we want to know then is, if we're going to do this thing where we're comparing to a reference value, we want to know if our sample is drawn from a population that's equal to a specific reference number. And so we might say, well, in the general public, the average serum cholesterol is a specific number. I wonder if my sample is drawn from a population that is the same as that, or if it's different. And so we're comparing each person to that reference value. A before and after is very similar to that, except that we're comparing each person to their own baseline. Now, before and after is the most common way we do this test, but it's not the only one. Conceptually, I think it's the easiest to understand, but don't get stuck just because something's not before and after that you can't use these particular statistical tests. In this top box, this is called a paired samples t-test, and it automatically capitalizes, so we'll fix that. A paired samples t-test basically measures every single person twice on that same variable. So let's say we're measuring cholesterol like we did in the one sample t-test, but instead of just measuring it once, we measure it once, and then maybe people go through a 6-week intervention where they learn about healthy eating and exercise, and then we measure that same variable, cholesterol, at the end of that 6 weeks. That hence why we call it before and after. So it's before and after some kind of an intervention. Now, if the paired t-test shows that there's a difference, because it's the same person, then maybe we can come to the conclusion that that intervention had at least part to do with why there was a change over time. So that's the paired t-test. And they're very similar to each other. Here we're comparing each person's measurement to a reference value. Here we're comparing each person's measurement to their own baseline. And so we're still doing this comparison. So mathematically, these actually behind the scenes are identical to each other, but we gave them a different name because people understand them to be used for different kinds of questions. Our next couple of tests are also similar to each other, and this first one allows us to evaluate whether two groups have the same average for a particular scale variable. So a good example of this would be whether men and women have the same average cholesterol. We've measured each person once, similar to the one sample t-test. However, we're splitting our sample into two groups. And so what we end up is something called an independent samples t-test. And it's called independent because these two groups are independent from each other. Here we measured twice, but those two measurements are not independent from each other. Each person's before is linked to that same person's after. But when we have these two independent groups, then mathematically this is slightly different than what we were doing with the before and after scenario. We can expand those two groups and say, well, maybe we want to know if public health students and medical students and dental students and pharmacy students all have the same average cholesterol. So instead of just having two groups, we have 3 or 4 or sometimes even more groups that we're comparing to each other. And so this is called a one-way Anova. And Anova stands for analysis of variance. And you think we're doing an analysis of means, but you'll see when we talk more about the one-way Anova why this is an analysis of the variance, so standard deviation and variance, rather than we're evaluating the means. So what I want you to remember is that the independent samples t-test is a special case of a one-way Anova where we're only comparing two groups. One-way Anova will look at 3 or 4 or 10 or however many groups we have, but the independent t-test is just the simplified version of that where we only have two different groups to compare for this continuous variable. And then we get to the scale by scale test. And this is where we start thinking about linear regression. Technically, simple linear regression goes into this box, but we're not going to be talking about that this week. We're going to be talking about something called Pearson Correlation. And Pearson Correlation is looking at the correlation part of simple linear regression. the best picture for a Pearson correlation is a scatter plot where you have an X and a Y variable, and then you have a cloud of dots going across that field, and you can see how those two scale variables relate to each other. A typical correlation that we like to think about is height and weight. If a person's weight changes depending on how tall a person is, which we know it does, then we would see this cloud kind of go up and to the right. So as a person gets taller, they also tend to weigh more. Now the second row is, I mentioned before, this is something called non-parametric statistical tests. And the reason we call it non-parametric is that we are no longer dependent on these parameters. Mean and standard deviation are considered to be parameters of this continuous or scale variable. Technically, everything that's below that line is non-parametric, but because we are kind of dumbing down the scale variable, it's not normally distributed, it doesn't meet the assumptions, it's a small sample size, then these non-parametric statistics come in handy. So you're going to hear that term, non-parametric statistics. I'm going to fill this in a little bit, and you're going to hear more about these particular statistical tests as you go through more of this mini lesson. This first one is called the Wilcoxon, and specifically it is the sign rank Wilcoxon. Wilcoxon made a whole bunch of different kinds of statistical tests, so sometimes it's important to specify which one. And the interesting thing is the Wilcoxon sign rank, because these two are similar to each other, remember, the Wilcoxon sign rank also applies here to the one sample t-test. So I'm going to go ahead and copy that and paste it over there. When we're looking at, instead of a before and after, when we're looking at two different groups, the name of this statistical test is called the Mann-Whitney. And a lot of times these are named after people who discovered them or wrote them down. Wilcoxon actually came up with a test that works here too. And I'm not sure if Mann-Whitney beat them to it, but his is called the Wilcoxon rank sum test. And so that can be really confusing. Make sure if you're talking about Wilcoxon that you include the sign rank part of this. Remember, this particular situation is where we only have two groups. If we want to expand that so that we have three or more groups, then we have something called the Kruskal-Wallis test, and that's the non-parametric version of the one-way Anova test. And similarly, Pearson Correlation has a non-parametric test. It's called Spearman's Rho. And this is a little bit interesting because here for Pearson Correlation, we're looking at a scale by a scale variable. As soon as one of these variables becomes not normally distributed or ordinal, then really we end up treating both of those variables as if they're more of a ranked comparison. So here with Pearson we have scale by scale. With Spearman's, technically we don't have scale, we have rank by rank. And so this is a ranked kind of an evaluation. So we filled in the top two rows. You're going to see more about all of those statistical tests. One of the things that I encourage my students to do who find this particular way of learning helpful is every few days just grab yourself a blank sheet of paper and draw a, 5 by 8 table, and see if you can fill in as much as you can about these particular squares. The more times you do this, the more familiar the names will be. And then think about each of the different statistical tests and what they do, specifically thinking about how do tests relate to each other. Here we have the independent t-test as our parametric test, and then the Mann-Whitney is the non-parametric version of that. So going through that in your mind and really forcing yourself to try to remember and see how much you can remember can be a really helpful way of learning this. Now we need to fill in a few more squares down here in the bottom. Specifically, we've talked about how we have this before and after. We have a paired t-test. Wilcoxon sign rank is the non-parametric version of that. But what happens when we have a before and after of a dichotomous variable? We actually have something that is a chi-square test, and it has a special name. It's called McNamara chi-square. So the McNamara chi-square is in this special situation where we have a before and after. Goodness of fit just tells us how well our particular percentages fit what we were comparing to a reference. The McNamara chi-square allows us to pair that. Like the paired t-test pairs the before and after, the McNamara chi-square can pair before and after, or it can be used in other ways. And then we have one more area to fill in, and that's this area down here. Remember how I said that these two at the bottom are quite similar to each other? This is actually quite easy to remember. We don't have to remember a whole lot of different names, because in all of these cases, the chi-square test of independence is the test that we would use for that. So the way I explain that is, here we have a grouping variable. This could be dichotomous, this could be nominal, this could be ordinal. The 3+ group could be nominal or ordinal. And when we're doing a chi-square, we're really looking at categorical variables. Those categorical variables could be dichotomous by dichotomous, and that's where we had this special case where we have the chi-square test of independence, and we can do odds ratio and risk ratio. As soon as we have 3 or more categories, we can have 3 or more categories by 2 categories, and that's what this box represents. So 2 by 3, 2 by 5. Here we have, similarly, we have 2 variables by 3 or more groups, so 2 by 3, 4, 5, 10, however many. So these 2 squares are really the same. And then interestingly, chi-square is so flexible that we can have say a 3 by 6 chi-square. We can use variables that have multiple categories, and we can still do a chi-square test. That's because when we're looking at each one of those cells, we're thinking about observed minus expected. And we can really do that across a really large number of cells. There's one more thing that I'd like to add to this before we finish the video. And that's that we have a special case here that also goes along with the odds ratio and risk ratio. And that's something called a Fisher's exact test. As long as we only have a 2 by 2 table, sometimes when we have small numbers, we would need to revert to a Fisher's exact test. Remember how in chi-square we mentioned that one of the assumptions is that each cell has an expected value of at least 5. Well, sometimes we don't meet that requirement. Sometimes we don't have very many people in our study, and Fisher's can be a really good backup in that particular situation. Fisher is specific to a 2 by 2 table, so it can't be used as easily in these other areas. So we're including it for the purposes of this discussion only in this one cell right here, the 2 by 2 cell. I know that's a lot of information. As we go through, we'll be reviewing this and looking at each one of those tests individually, but I wanted you to get a bird's eye view as a starting point so that you knew where we were headed. In the next few videos, I'm going to be sharing with you several things where I talk about paired t-tests and Wilcoxon sign rank, independent t-test and the Mann-Whitney, the one-way Anova and Kruskal-Wallis. We'll talk more also about the McNamara chi-square, a little bit about chi-square test of independence and Fisher's, and then we'll also have a discussion about Pearson correlation and Spearman's rho. So we're kind of headed in the direction of explaining these in more detail, specifically explaining how you perform those tests and interpret the results in the SPSS computer program. So keep this handy where you can kind of keep an eye on it. Remember that I've intentionally arranged this table so that it would be easy to see how certain things are very similar to each other. All of this top row is considered our parametric tests because they all have a scale outcome variable. As soon as you have a dichotomous outcome variable, then you would be limited to doing things that are on this bottom row. So hopefully this can help you make those kinds of decisions as you're going through and answering research questions. Thank you so much for joining me.